Yeah, okay. So the recording for today's session has begun. Um, so once again, I welcome all the attendees. And my name is Jyotishwaran. I'm a PhD student from the EC department of the Indian Institute of Technology, Roorkee. And this is the discussion session for the physics of the nanoscale devices NPTEL course session for week 6. So, in this, we shall be concentrating on the contents of the lectures in week 7 of the course. But, however, if the attendees have any questions or queries and any other doubts from the previously covered topics, they shall also be dealt with during this discussion session. So, with that, does anyone who's attending this session have any questions or queries from the last week's content or the stuff before that? Any issues with the assignments? Anything that you'd like to have clarified?
Excuse me, sir.
Yeah.
Sir, I just want to know if
Mm-hmm.
Fermi direct integral means an
Yes.
important topic, or I could just look over it from up and leave it.
Okay, so like, see, you will not. I can tell you this much: you will not be asked to evaluate Fermi-Dirac integrals in your exams. Okay, but you should
Okay.
remember what kind of Fermi-Dirac integrals will appear where. So, since you've asked this question, I will briefly go over this in today's discussion also, because today we shall be looking, like we shall be summarizing the model of conduction once and for all, dealing with the ballistic diffusive cases, introducing the notion of mobility, and as well as talking about realistic 2D and 3D channels, sorry, 2D and 1D channels. So while we are doing all of that, yeah, we shall be looking at the Fermi integrals also. So what I will tell to everyone is that you will not be required to evaluate the Fermi-Dirac integrals themselves, because of course, as was mentioned in the lecture, those integrals are usually solved numerically. So that part is not asked for. However, you should know which kind of integrals will appear in which kind of expressions. Like if I'm asking for a current flowing through a particular channel, then you should know what kind of a Fermi-Dirac integral will appear there. And to know that, it's pretty straightforward, but I will tell you how to do that step by step also. So if you know that, then you
Okay,
should
sir.
be fine with dealing with questions regarding the Fermi Dirac integrals. And I shall also like talk briefly about the Fermi Dirac integrals to begin this session with. So that is that. Any other attendees have any questions? You can ask from any part of the course that has been covered so far. Well, okay, one just left. All right. In that case, let us begin with this week's topics. So, yeah, just one second. Yeah. So, yeah. So, yes, as Ichanshu asked, let us start with the concept of Fermi-Dirac integrals. So, now what are these Fermi-Dirac integrals called? So, in general, a Fermi integral or a
Sir,
Fermi. Yeah. Oh, sorry,
screen
sorry. I have
sharing
not
is.
shared. Yes, yes, yes. I just realized that as you mentioned it. Apologies. Uh, yeah, is the board visible now?
Yes, sir.
Thank you. So, yeah, in that case, let me start from the first because it's also being recorded. Yeah, so we have our Fermi integrals. So standard notation is we use a script F. Yeah, just one second. I think we have a new attendee. Okay, yeah, there's back. Yes. So in general, we shall write the Fermi Dirac integral f n of, so how shall we call it? Yeah, so it is usually parameterized by a quantity called eta f, and this is an integral over the appropriate range, uh, eta to the power n divided by 1 plus exponential eta minus eta f. So d eta. So this is, yeah, this is the Fermi Dirac integral. Now this might look somewhat abstract to you, but if you take the Fermi function, which, just one second, yeah. So if you look at the Fermi function, which is f of e, which we write as 1 over 1 plus exponential of e minus ef upon kbt, then what we are essentially doing is we are setting a new parameter eta that is defined as e divided by kbt. So this quantity is a, like, kbt has the dimensions of energy. So this entire quantity is a dimensionless quantity. So it kind of like scales the energy. Therefore, the Fermi energy will be replaced by, will be transformed into a quantity eta f, and that is the quantity that is appearing here. So this is the Fermi function essentially integrating with an energy parameter raised to the power n. So there are several relations to this. We can talk about the derivative property of the Fermi integral. We can talk about the relation of Fermi integral of order n. So this quantity n is the order. It's the order of the Fermi integral. So, and there are several standard results for this. Uh, so from the people who are attending I mean this session, do you know what the value of Fermi integral 0 is of eta f? Are you guys familiar with this?
No, sir.
Okay, then let us do this. So what is this integral according to the previous definition? I mean, the definition is right here. All you have to do is substitute n to be
1
0.
upon
Exactly, it
1
is 1.
upon 1 plus e raised to eta
Exactly.
minus eta f.
So exponential eta minus eta f. Okay. So d eta. Now, what is this? What is this integral? Like in the appropriate range of energy, that is what I said. So this is very much a definite integral. It's not an indefinite integral. So in this case, the range is usually listed as 0 to infinity. So now what is this integral from 0 to infinity? Can anyone tell me? Like this, you guys should be able to tell me right away. This integral is 1 because this is the area under the Fermi-Dirac distribution function. Is that clear?
Yes, sir.
So, because this is essentially just the area under the Fermi-Dirac function, and as we have discussed before in our previous week sessions, the area under the function is essentially the total probability of finding an electron with any energy. Now, if an electron exists, of course, like it has to have some energy, and therefore finding an electron with any energy, the probability of finding an electron with any energy is 1. So that is essentially what this quantity means. So um, the zero order Fermi integral has a value 1, and so from this you can like proceed to evaluate other Fermi integrals. So if I not if I mean it is also possible to have a Fermi integral of order half. Let me just make this as curvy as possible. Yeah, Fermi integral of order half. So that would turn out to be integral of order half. Yeah. So Fermi integral of order half can be approximated using, or rather, let us not talk about Fermi integral of order half. Like you can look at the slides. I do not want to spend too much time on the Fermi integrals because, as I mentioned, solving these integrals is not important. You just have to remember what integrals appear where. You don't even need to remember the exact value of these integrals. By and large, for the what to say, like solving the questions in this courses assignments and examination. So before that, yeah, let us so yeah, in week seven's assignment, which is due 4 days from now, I don't think there are any questions based on the Fermi integral. However, if you go back to say week six, I think there are one or two questions. Uh, Maybe. Oh, okay, not even here. Yeah, there is just this one question, but this thing was what to say, like shown in this part was done in the lecture, so it is just a question of variable substitution. So yeah, the questions for Fermi integrals will essentially just be conceptual questions. They will not be numerical questions. So because of that, I will not spend too much time in our discussions also because it does not serve any significant purpose. All right.
Okay, sir.
So, sorry. Yeah. My God. Yes. So this is the point. Yeah, there are other relations and recurrence relations for the Fermi integrals and so on and so forth. Now, where do these Fermi integrals appear? So with that, we will start our discussion for today in earnest. Uh, Now, where do these integrals appear? So let us start with the most familiar case of uh, current in a oops, ballistic channel. So this integral, as we have done several times before, now we are also assuming for a small bias. So if there is a small bias, what happens? Can someone tell me like what would I use?
Sir, then we can use Fermi window function.
Exactly. Or, oh, no, 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 I should not use the small bias case here because I need the Fermi Dirac integrals. I'm sorry. General bias, not small bias. Apologies. Yes, but you are correct, Chanshu. In that, if we have a small bias case, then of course the Fermi window function appears. But we are not looking at the small bias case. We are looking at the general case, so that will give me. Why did I do that? Yeah. So we have 2q upon h integral m of e, which is our total modes times f1 minus f2 de. Now, of course, f1 minus f2 times uh, oh, yeah. Now I realize my mistake. No, it is actually for the small bias case. Let me just quickly go back and change one very important thing. Hmm. Yeah. So there is also an exponential factor appearing over here that will also be present. So I will have exponential. Let me just clarify that from the slides. We can just look at that and put an end to this thing straight up. So okay, so the previous week it should be covered. Oh no, it's just eta bar j. Then how did he? No, so our definition was fine. Uh, and how do I match these two integrals? What am I missing here?
Sir, I think we take temperature greater than 0 Kelvin.
Mm, no, like whichever case you take, the formula, like the Fermi integral, essentially has to hold. The point is when I am what is it like taking a small bias and like when I'm taking the small bias case, I will automatically get a an exponential term. So that's what I'm wondering how to like how that is usually dealt with. Can you guys tell me where the Fermi integral was first dealt with? Was it in week 6 or week 7?
Sir, in week 6, lecture number 29 or 30.
Okay, 20. So either the last or the second last, right?
Yes, sir.
Yeah, so this is how it goes. These are how the Fermi integrals are defined. Uh, and now, in order to do that, okay. They are written as derivatives of the Fermi integral. Fair enough. And then they use the derivative property. Yes. Fine. Yeah, sorry, I got confused. Let us. Apologies. Yeah, nothing needs to be changed here. I was remembering things correctly, so uh, sincere apologies for. No, why are you not picking? Yes. So yeah, sorry about that confusion. So going back and opening. This one. Why do you have to auto center? Always. Yes. So coming back, yeah, originally what I mentioned was correct. So we are considering the case where I am looking at the low bias approximation. So in the low bias approximation, this whole thing is replaced by essentially 2q square m of e f by dou e dE. Is this correct? Hello.
Yes, sir.
Yeah, so is this expression correct or have I made any mistakes?
Sir, TE term is also there.
No, ballistic. That's why I said ballistic. See, for ballistic cases, T is 1.
Yes,
So is this expression correct?
yes, yes, sir.
Well,
No, sir, that q square, it will be 2q by h, na?
no, no. Okay, the thing that I've actually missed is the potential times V. So it is this entire integral times the potential. Because when I do the Fermi window approximation, the bias has to jump out, right?
Yes, sir.
The quantity in the brackets is the conductance. So this is the quantum of conductance, this is the mode integral, and this is the applied voltage. Okay, so now, of course, since these two derivatives kind of act on, well, what we should remember is that originally this was not dou f by dou e. This was dou f by dou ef. So, and there was a negative sign here. So, for that purpose, let us go back to that. And now, since this partial differentiation and this integration are taking place over two different variables, I can kind of do them in whichever order I want. I can do the differentiation first and do the integration, or I can do the whole integration and then take the derivative with respect to EF. So, what I'm doing is I'm choosing to do the latter. So we have dou by minus dou by dou EF times this entire quantity, which is 2q squared 1h integral m, m of e. Yeah, just 1 second. I think we have a new attendee. Oh, yeah. Hello, Kamal.
Yeah, good afternoon, sir.
Good afternoon. So, yeah, carrying on with our session. Uh, just 1 second. You should be in the other lab. Yeah, so continuing. Now, this quantity is now, since I'm doing the derivative on the outside, what I'll just have is the Fermi function over here. dE times the applied bias. Of course, we have to remember that this is a small voltage. Small compared to what? Do you remember? This was discussed last time. So it should be small compared to the Fermi level. So that is what we mean when we say that the applied bias is small. So now, what do we know about the modes? Does M of E have an energy dependence? for different types of channels. What is M of E for a 3D channel? Like, what is the energy dependence? Is it proportional to the energy? Is it proportional to the square root of the energy? Or is it independent of the energy? What is it? Someone? Anyone? Yeah, you guys are all here. Uh, I'm audible, right?
Yes, sir.
Yeah, so can, like, do you guys remember these things? Like, this was what, week 4 or 5? It's not too old, also.
Sir, no, don't remember it right now.
Oh, that's fine. Okay, fine. Yeah, so if you guys don't remember, you can tell me again. As I've been mentioning since the beginning, not knowing an answer here will not get you penalized. So you don't have to worry. And only when you answer something correctly will I, what to say, like name you guys. So if you're worried about people watching the video thinking that you don't know things, when you guys don't answer something, I will not name people. If you have observed, I follow that practice. So your identity is also secure. And when we are discussing these things, only the board is visible. So people can't see who's talking and who's not talking. So if you don't know something, just say you don't know so that you know we can move on. So just like the density of states, which had differing energy dependencies, the modes also had different energy dependencies. So what you will have found out is that the modes are actually proportional to e to the power 0, e to the power half, and e to the power 1. In the case of density of states, we had e to the power minus half, e to the power 0, and e to the power half, whereas in the case of modes, we have this. So now that I've given these three values, can you guess what are the dimensions of the channels here?
Sir, for one dimension, it will be raised to 0,
Exactly,
and for
because this
2D half,
calculation we have done to show that it is a constant. So yes,
yes,
this
sir.
is a 1D channel, this is a 2D channel, and this is a 3D channel. Okay, so and oops, channel and ditto. I should have put a ditto in the previous case. So now, yes, that implies there is an e term or an e to the power half term or no e term with some more constants. Correct?
Yes, sir.
Now, all of those constants I can pull out. So what will I be left with? I will be left with either e to the power 0, e to the power half, or e to the power 1 multiplied by the Fermi function integrated over the energy. And that, by our definition of, by the things that we have seen in the previous slide, is just the definition of the Fermi integral. Like, can you see that? Once I pull out all the constants that show up in the modes function for different materials, there will be different kind of constants. So once I pull out all the constants, I will only be left with the energy terms. So the energy terms are either e to the power 0, e to the power half, or e to the power 1. So in any case, what I will be left with is minus dou E by
Difference in
what?
yeah, difference in like Fermi functions.
Oh, so this is for the small bias case. So the difference
Okay, sir. Okay,
vanishes. See,
right.
this is what I'm starting from. Okay. So I already use the Fermi window over here. So this is the Fermi window function. And I am recognizing the case that the differentiation is happening with respect to EF, and the integration is happening with respect to E. So I can do these two operations in any order that I want. I can perform this entire integral and then differentiate it with respect to EF, or I can take the derivative and then do the integral. So both are allowed, both are valid. So what I'm choosing to do is I'm choosing to do the latter. So in that case, what will happen is I will get a bunch of constants which I'm not addressing right here because as you will see in the assignments, they will not be required. And then I will have an integral that is essentially e to the power m divided by 1 by 1 plus exponential e minus ef upon kbt de. So now this whole quantity is again multiplied by the bias. Now I know this integral by what we had discussed previously can be identified as a Fermi-Dirac integral.
Yes, sir.
Okay, so Fermi-Dirac integral. Now, what can the values of m be? What are the possible values of m? I mean, I've written those right here. It can either be 0, half, or 1.
Yes, sir.
And well, if we are being very precise, then I will also add another row to this just for the sake of completeness. However, you will notice that we will not be dealing with those cases because of some other issues. So e to the power half, oh sorry, e to the power 1. Now this is a 3D channel. And if I were to ever calculate the modes for a 0D channel, I will get an e to the power half dependency. But you will notice that when we did the modes calculation, uh, we did not talk about the 0D channel. Can somebody guess why?
Because, sir, uh, terms like conductance and all will be useless for a zero D channel.
Why? Come on, I can have a what to say like atom in between, and see that is the whole point of us discussing the quantum of conductance. That even when we consider quantum mechanical transport, there is a non-trivial resistance, and in fact that resistance is not even small. It is around 13 kilo ohms. So the same constants will appear for a zero D channel as well. But somehow we don't do the modes calculation. So the reason for that is actually because if you look at the broadening parameter, we usually refer to, see in all these three cases, we would have calculated this quantity Vx plus. Do you guys remember in our derivations?
Yes, sir.
So this concept of velocity actually does not apply to a zero D channel. It's not because conductance doesn't apply, it's because motion does not apply in a zero D channel. So this
Okay, sir.
is generally not used. We use different models when we consider zero D channels. And in the case of zero D channels, like even if I have a quantum dot of some significant dimensions, as long as I'm treating it as an artificial atom, you will notice that we will no longer be talking about the ballistic motion of electrons through them. Because when we are talking about a quantum dot, we have to treat it as a purely quantum mechanical channel. So that is the reason why this whole ballistic model does not fit. Like essentially, when we talk about zero D channels, typically we will not be talking about the ballistic conduction model. So model is not used. However, you are free to do the density of states and the modes calculation, you'll find that whatever the equivalent of modes are will actually have something like an e to the power minus half dependence. But of course, those are not proper derivations. So that is why this thing was there. So now let me get rid of this to avoid any further confusion, because the final version of the slides will be shared. People watching the video will be aware of the discussion that we've just had. Apologies. Yeah, so in this case, what are the possible values of m? M is either 0, half, or 1. Correct?
Yes, sir.
Yeah. Uh, someone joined? Okay, it's fine. Yes. So 0, half, or 1. Now, what we will notice is that, yeah, outside of these constants, finally there is also the derivative. Now, the derivative property, if as we saw in the slides just now, over here, yes. So let me just open this up here. Zoom in. Yeah, no, zoom out slightly. Yeah, so what has he spoken about? Yes. So whenever I take the derivative of a Fermi-Dirac integral, what will happen is the order will be reduced by 1. Okay.
Okay, sir.
Like I will get another constant and the order will go down by a factor of 1. So if I take, oh, sorry. If I take the case m equal to 0 and then do this derivative, I will be left with Fermi-Dirac integral of order minus 1. For the case of half, I will be left with a Fermi-Dirac integral of minus half. And for the case of Fermi-Dirac integral 1 in this term, I will be left with if a final Fermi-Dirac integral of order 0. So for my 1D channel, I will be using, for the current, I will be using f minus 1 of eta f, and for my 2D channel, I will be using like in the resultant expression, we shall be using the Fermi integral minus half of eta f, and for the 3D channel, we shall be using what we'll be using for the 3D channel?
0.
Yeah. This is for the current. Now for any other quantities, again, look at the initial integral, follow the same steps. Ultimately, there will be a differentiation, a bunch of constants, and a previous Fermi integral. Now, wherever you have to do the differentiation, reduce the order by 1. So this is all you have to remember. For what kind of a channel, what kind of a Fermi integral you will need. So if I somehow like questions will be like this. If I were to try to calculate the say current to conductance ratio for some general uh, not current to conductance, current to charge ratio, then you will notice that like just like I have the current integral here, there is also an integral for the charge, correct?
Yes, sir.
And over there also the Fermi function appears, and you can use it to like approximate that for the small bias cases as well. So you can again get a similar expression like this for the stored charge in a channel. So similarly, you will get a bunch of results and a bunch of Fermi integrals for that. So questions will be like, okay, so if I'm taking the ratio between the current and the charge for a channel of a certain kind, what will be the ratio of the Fermi integrals that I will see there? So you're just supposed to identify what integral will appear in the numerator, what integral will appear in the denominator. So that is all the working out you will have to do for this case. So those will be the questions pertaining to the Fermi integrals that you will encounter. Okay. So with that, I think we have discussed enough with Fermi integrals. If you have any further questions later on, of course, we shall deal with them. Uh, so yeah, moving on. Now let us talk about, like, this is the part that we left out last week because of the lack of time. So essentially, we shall talk about the ballistic to diffusive transition. Of course, now you guys have seen the lectures, so I can quickly walk through this. So when I'm looking at diffusive transport, what is the model I use? What is the current density equal to?
Sir, I by W.
No, I by W comes later. Like if I'm talking about the diffusive model, it's minus dn dn of x upon dx. Is this correct?
Yes, sir.
Essentially, current flows from a high charge concentration to a low charge concentration. So if I'm moving along a particular direction, and if the charge concentration is increasing, the current will flow in the opposite direction. If I'm moving along a certain direction and the charge concentration is decreasing, then the current will flow in that direction. That is essentially the model for diffusive transport. So essentially, if I have a charge carrier profile like this is x and this is n of x, then, and like this is the positive x direction starting from 0 to some point L, then the current will flow. Oops. Will flow. Still looks like how? Come on, it's not fair. And yeah, since I've started erasing things, I. So which direction will the current flow in this case? Positive x or negative x? Someone? Anyone?
Sir, NX is number of electrons.
Yeah. Not just number of electrons, it is the charge density. It has the charge in it. It's not just a number function. Okay, tell me this. Which direction will the electrons move through diffusion? Forget the current. Will the electrons move from, like, will they go from 0 to L or will they go from L to 0?
So 0 to L?
0 to L.
Yes, 0 to L. You're correct. In that case, what is the direction of the current?
L to 0.
Yes. So, what will be the sign of the current in that case? Positive or
Negative.
negative? Huh? Negative, yes, you're right. So is the equation that I've written there consistent with that? So that is why I said n of x is the charge density. This is not just the number density. So n of x is always a negative quantity. Okay, so when I write this graph here, this graph actually shows just the number density. But this is always multiplied by the electronic charge. So there is a negative number already in this end. Okay. And
Yes,
since
sir.
the slope is decreasing, there is another negative quantity. So those two negatives will multiply with each other and this quantity will become a net positive. Okay. And then multiplied by minus dn, I will get the actual correct negative current that I'm supposed to get. Is that clear?
Yes, sir.
Yeah. So this is the thing. And then, so what is the transit time? Tau for the diffusive model of transport. Comes out to be L square by 2dn. So this is tau diffusive. And then you have tau ballistic. What is tau ballistic? You guys remember this?
No, sir.
No. Okay, that's fine. Totally all right. So, I mean, go through the slides. Uh, Although
Yes,
there
sir.
may not be questions directly with this, it is good to remember and understand these things. So tau ballistic is L by the quantity that we talked about before, the positive average positive velocity. Like this part, we have discussed in our session also. The tau diffusive, I am not deriving. Okay, like it is possible to derive that, but I'm not deriving it here. Okay, so then essentially what we do is we consider the ratio between these two quantities, and then we can find out that uh, tau. What is it supposed to be? It is supposed to be tau ballistic by tau diffusive. Yeah. So tau ballistic by tau diffusive. Like after all the necessary derivations, you will find that this quantity is equal to lambda of E divided by lambda of E plus L. And this is called the transmission coefficient, T of E, which Chanshu, if I'm right, you mentioned should appear in the current integral. Correct?
Yes, sir.
Yes. So now, and is this expression correct?
Yes, sir.
Good. So finally, if I have to write the generalized current, so now I don't have to say the diffusive current because this factor will take care of that for me. Okay. So, yeah. So now the total current is 2q squared upon h integral T of E M of E. And let us consider the small bias case only. So dou F upon dou E dE multiplied by V. So this is the total current. Now this quantity is this accounts for the diffusive transport, that is the channel length. So this accounts for the diffusion effects. And modes, of course, is a quantum mechanical thing, and then we have the total integral. So tell me this, as L keeps increasing, what happens to this quantity in here? As we have discussed before, this quantity in here is the conductance. So as L increases, what happens to this quantity? Does it increase or
Sir,
does
it
it
decreases.
decrease? Exactly. So if L increases, and of course, let me clarify here, positive x direction, and let me say L is the channel length. So if, yeah, coming back, L increases, G decreases, which kind of makes sense, correct? Because forget even diffusive transport model. Way back when we look at the ohmic transportation model, what is the resistance directly proportional to? Like R is
Sir,
equal to
L.
what? Yeah, R is rho L by A, correct?
Yes, sir.
Yeah, so let me just stop presenting briefly. Yeah, so R is rho L by A. So when I'm increasing L, the resistance will increase. Since the resistance is increasing, the conductance will come down. Now, what does A change? A, if I increase A, the resistance is supposed to come down, correct?
Yes, sir.
Now, when I increase A, what else does change? Like what other quantity changes? Something familiar to the ballistic transport. Like does the channel width change if I increase the cross sectional area?
Yes, sir.
Of course, like the channel
Actually,
width will
because for
increase.
2D, yes, sir, for
Yeah.
2D WL ratio is there, na, that's
Yes. So if I'm increasing the area, like the cross sectional area for a 2D channel, increasing that implies only increasing the width. For a 3D channel, there will be a width and a depth. So I will increase both of those dimensions. So in that case, what happens is even in the ballistic model, the number of modes increases because in the previous
yes, sir.
discussions, we have seen that the number of modes is just the number of half wavelengths that fit into the width. Okay, so at a particular energy is the number of half de Broglie wavelengths that fit into that particular width. So if I'm increasing the width, the number of modes are increased. So since the number of modes have been increased, I have more channels for my electron to move from the source to the drain. So increasing the width, which is corresponding to increasing the area, will lead to an increase in the conductance or a lowering in the resistance. So the model that we have defined here, yes, while it includes us dealing with several new fundamental concepts, we are considering quantum mechanics, we are considering diffusion, we are considering, carrier statistics and all these things. At the end, the net behavior is virtually identical to an ohmic resistance. Increasing the length will increase the resistance, increasing the cross sectional area will decrease the resistance. And you will also find out that increasing the temperature will increase the resistance. So these are, yes, this is a different model that we have, what to say, like introduced and studied, but the net effects, materials, the nature of the material is not changing here. This is not like studying some new phenomena like superconductivity where the behavior of the material itself changes. Not quite. Here, yes, quantum behavior does manifest, but the overall current voltage relationship and relationship to resistance and conductance and geometry remains the same. All right.
Yes, sir.
So I hope you guys can
Yes, sir.
appreciate that fact. All right. So now moving on, let me resume the presentation. So yeah. So what I shall do now is for week 7, I'm not again, as I mentioned before, I shall not be discussing the assignments, but again, you will notice that the time for conceptual questions is kind of like reducing gradually. So we shall look at the questions here and then talk about the necessary concepts and also do some examples. Okay. So for that, I will need the help of the guys who are attending this session. So, as and when we are crossing these questions, just tell me if we have, forget the lectures, tell me if we have discussed the necessary concepts for solving these questions. Okay. So, look at question 1. You guys can see the assignment, right?
Yes, sir.
So, now they are talking about average power dissipation and whatnot. Now, this part we will come to later. So, something more needs to be discussed over here. Uh, what about question 2? Like, essentially, we are talking about. So, have you guys seen assignment 7 yet, or are you guys yet to see
No,
it?
sir.
You've not seen it. Okay, in that case, let me just quickly say that for most of the question, you guys like we need to discuss a couple more ideas. So before that, yeah, since Kamal, you joined a bit late, do you have any questions from the previous assignments and topics that were covered?
Yes, sir. Actually, one question I have.
Okay, yeah, go ahead. Ask
Maybe
that, and
maybe
then
that you covered in the last week or not. I don't know because actually we
that's
have
fine. That's
some
fine.
semester exam. That's why.
That is fine. That is fine. You
Um,
can go ahead and ask the question.
yes, sir. Sir, my question is like that. We already discussed everything about the ballistic cases from current calculation, like transit time, everything. Now we are
Yes.
moving through the diffusive transit. So how
Yes.
this transition actually happens from ballistic to the diffusive? This question is coming in my mind while learning
Okay.
through the
Okay.
diffusive transport case.
So,
Why the condition
yeah.
is changing from ballistic to diffusive
Okay.
like that?
All right. So consider the so yeah. Since I wrote ballistic to diffusive transition here, we are supposed to discuss something about the transition as well. So yeah, thank you for bringing that point up. So one. So now let us look at our good old friend, the two-terminal device. I have a source, a channel of like whatever geometry and structure, and a drain. My channel lies in between. Now, so tell me this. How did we find the, what shall I call it? Yeah. So we had calculated this quantity, n. N is equal to what?
Number of turns in the channel, sir?
Yeah, what? Hello?
Yes, sir. Voice is
Yeah. N is the charge stored in the channel. So what are the terms that appear here? Just tell me that. Is this correct? Hello? Anyone? Someone?
Yes, sir. Yes, sir.
Yeah, this is correct, right? Or am I missing some factors? Feel free to chime in.
Wait.
I mean, if you guys have any notes or if you can open stuff and look, just look and let me know. You know what? I'll also look. I mean, uh, what's the harm?
It's right, sir. It's right.
That's correct. Like
Yes, sir.
no pesky little factors. Mhm. Yeah, it's actually correct. So yes, going back. Now this is what we write. So what is this? Is this the total? What is this? Like what is the unit of this quantity? Does it have any dimensions? Okay, the answer to that question is there are no dimensions here. Like density of states is the number and this is a probability. So when I do the integral, the resulting answer is also just a number. Okay, so this is the number of electrons in the channel,
The channel, right, sir.
number of stored electrons to be precise in the channel. So under a particular bias condition, what will happen is a certain amount of charges. So let me represent it like this. Let me use the let me use the blue and the black. So when I'm applying a voltage, so when I'm applying a bias, which we shall call V, then of course as the bias is applied, there will be a certain number of electrons that will be moving from the source to the drain, correct?
Yes, sir.
Okay, but what is essentially happening is what is also happening if we are looking at the band structure, like since yeah, when I'm looking at the band structure, what I will see is that the uh, yeah, I will have the Fermi level EF of the source, and then I will have my channel energy levels, and then can I move this guy elsewhere? No, I can't. Okay, but I need it. Oh God, this is a bother. Yeah. So I have my channel which I am discussing, I mean, talking about in terms of some finite collection of energy levels. There is broadening and all of those things happening here. And essentially, I have EF source and EF drain. And I have like electrons below EF. So what will happen is my electron from the source will jump in here and then jump out into the drain. Correct? That is how uh, current is. Oh, sorry. Yeah. So technically speaking, electrons will move in the opposite direction. I should have. Yeah. If I'm like talking about current, then of course current moves this way. But if I'm talking about electrons, electrons move in the opposite sense. So so yeah. So electrons will be moving this way, right?
Yes, sir.
Okay. But when I'm doing this, like when I'm setting up a bias, it is also possible for some electrons to enter the channel and remain static. So that is what we call as stored electrons. Okay. So over here, the blue dot corresponds to mobile electrons. So these are what we call as charge carriers. Mobile electrons or holes, as we shall see later. Like currently, we are only talking about the conduction band in our discussions for reasons that will be made clear later. And these are the stored electrons. So these do not have a kinetic energy. They are, for all intents and purposes, confined within the channel by virtue of the voltage that I have applied between the source and the drain. So that implies now there is a, now let us say this is a 3D channel. Let me assume it's a 3D channel. Or rather, let me write in black itself. So assuming a 3D channel of volume V. Okay. Okay, now V is not correct. Volume, what shall we call it? Yes. Can you suggest a good variable for volume?
Sir, V.
No, V have already used for voltage. Come on. You know what? Let me call it. Let us be fancy.
Sir,
Let me.
V naught.
No, V has been given to voltage, so let us not use the letter V. We are educated people, so let me call it capital gamma, which is also a quantity that is used for volume. Okay, of volume gamma, and this channel has length L, so it has some cross sectional area. Okay, so now that implies I now have a quantity n by gamma, which is equal to what? The carrier density, or rather the electron density, I shouldn't call it the carrier density.
Yes,
I
sir.
have a stored charge density. Okay, this is the stored charge density. Now, the question is, how does this charge density vary across the length of the channel? Like, is it constant? Is it increasing? Is it decreasing? How will it vary in general? Any clue? Any hints?
Sir, more near the drain and less near the source.
Always.
Depends
No,
on
sir,
channel, sir.
in this particular condition.
Okay, yeah. So essentially, yes, what you're saying is correct. Closer to the drain, I will find more stored charges, and closer to the source, I will find lesser stored charges. That is a fair assumption to make. But now, what will be the difference in this variation? What will that depend on? How much will the stored charge differ by from the channel drain interface and the channel source interface?
Sir, the
Depend
amount
on
of potential we give.
Yes, it depends on the potential A, but we are using let us say we are considering the small bias case, so V is very small. The second thing that will matter here is now the channel length. Now, if L is large, the difference between the stored charges at both the interfaces will be high.
Yes, sir.
For a large channel length, stored charge density will have a larger variation.
sir large channel length example like 60 to 70 nanometer length there.
We'll see what is large.
Okay, sir.
We'll,
Okay.
we'll also see that variation in the channel. So since there is a larger variation of the charge carrier density, or rather stored charge density in the channel, there will be a diffusive current now. Is that clear?
Yes, sir.
So now that
Yes, sir.
diffusive current will kind of oppose, or not oppose, the diffusive current will start contributing to the total current flowing through the channel. The greater the
Yes, sir.
length, greater the charge carrier disparity, not charge carrier, the stored charge density disparity, and more the diffusive effects will show up. So that is essentially where we have a transition from the ballistic to the diffusive transport models. And also, additionally, another thing, in the assumption of ballistic transport, we say that the electron moves without suffering any collisions. Now, what will happen is, as and when there is a charge carrier concentration, the electrons, a stored charge concentration, the electrons may scatter with those stored charges also. They may interact with them. Okay. So that will also have an effect on the current flowing through the channel. So the larger the channel, the more the stored charge density, and therefore not more stored charge density, the more the disparity, the variation in the stored charge density, and because of that, I will have stronger diffusive effects. So that is essentially, and we through our derivations have seen that the transmission coefficient T of E is
Yes, sir.
lambda of E divided by lambda of E
Plus.
plus L. So as L increases, T of E becomes smaller and smaller and smaller. Now you are asking what is the ideal values of L. So for that we have to ask ourselves, what is the typical value of the electron energy? So take a material like silicon. Okay. Now what is the band gap of silicon? Eg of silicon?
1.1 V.
Yeah, 1.1 eV. So the Fermi level is usually situated at the middle of the band gap.
Yes, sir.
So at the bottom of the conduction band, the electrons have an energy of roughly half an electron volt above the Fermi level. Correct?
Yes, sir.
So what is the and assume that the effective mass is the same as the electronic rest mass. So now tell me what will be lambda e corresponding to half an electron volt? Can you can you guys calculate that and tell me? So for oh sorry yeah uh, for or why half an MeV? Let us take some half an EV. Let us take something like 10 EV. What's wrong with that? No, 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 no. And let us actually take half an EV because for 10 EV it will actually come down. So for 0.5 eV, which is typically the electron energy we will find if silicon is the material with which we are manufacturing our devices, lambda of E is approximately 1.8 nanometer. Is this clear? Like, I mean, why am I asking is this clear? This is something that I just calculated. So, essentially, lambda E will be of the order of a few nanometers, no more. Okay. So, this can approximately be somewhere between, so lambda of E, by this calculation, we know that it is somewhere between 1 to 10 nm. Okay. So any channel length that is significantly larger. So that is, say, if L is at least 5 to 10 times of lambda E, then I will have ballistic effects. Is that clear?
Yes, sir.
So for this case, for this particular case, even a channel length of 10 nanometer will show ballistic diffusive effects. Sorry, why did I write ballistic effects? Diffusive effects. I'm really sorry. So I will have diffusive effects. So ultimately, what you are supposed to ask is what is the characteristic energy of the electron in the channel. Depending on that, you will get answers for what kind of channel length will you be able to find what to say ballistic mode of conduction and where you have to take diffusive effects into consideration. Is that okay? And typically, yes, I think Kumar suggested that it should be something around 60 to 70 nanometers, correct?
For diffusive case, na sir?
Yeah.
Yes, sir.
Yeah, so typically in that case it is fine. 60 to 70 nanometers, you can. So usually in the questions that is being asked, a characteristic energy will be mentioned, like the energy of the electron, or the temperature, something will be mentioned. If the temperature is mentioned, then take E equal to kBT. Okay. So yeah, let me quickly go to a new slide and write those things. So what are the characteristic energies? So characteristic energies. So the first characteristic energy we have in the channel is the Fermi energy. Okay. Now this is a constant that is usually given beforehand. You cannot derive the Fermi level or anything. You're supposed to, like, it's experimentally found out. And this is information that is given to you before the beginning of the problem. Or you can be given the temperature. In which case, another characteristic energy can be written as kBT. So this is the average thermal energy. Are you guys familiar with this? Yes or no? Someone? Anyone, please?
Sir, means we are using it from a long time in this course, but matlab, uh, like
Mm-hmm.
not familiar other than that.
So that is enough. Like, so you know that this is an quantity that is equivalent to energy, right?
Yes, sir.
And then you can directly be given the kinetic energy of the electron. So what you are supposed to do is, for either of these cases, you calculate lambda of E. Okay, which is what? H by square root of 2 m star E, non-relativistic cases. And I mean, that is all we are considering here. Are you guys familiar with this relation?
Yes, sir.
So now once you find out what lambda E is, that should tell you what the characteristic length, the characteristic wavelength of your electron is in the channel. So now depending on that, you can guess if the given channel length is small or large. And you can decide whether to use the ballistic model, or after this you compare lambda of E with the channel length. If lambda of E is greater than L, then you can directly use the ballistic model. There are no issues there. If it is too small, then that's a different question. But if it is just small, it is fine. And if lambda of E is approximately in the range of L, then you are supposed to use TE in the current integral. In the current integral. So here T of E is set to be 1. And for the third case where lambda of E is greater than L, again the same is used, but we acknowledge that ballistic effects are predominant. Okay, is this clear?
Yes, sir. Yes, sir.
Yes, sir.
Okay, so this is so when solving problems, this is all you have to do. Typically, the energy that you will be dealing with is the Fermi energy. At least the questions that I have made, I will either give you the Fermi energy or in last week I gave a technique where given the charge carrier concentration, you can find the Fermi level. Uh, uh, Ichanshu, do you remember that you were there last week? So I'm asking you.
Yes, sir.
So use that technique to find the Fermi. Sorry, it's not Fermi function. Indirect Fermi function. So this is the Fermi level.
And sir,
Yeah,
uh, I not found your videos in that site.
you should be finding it now. There
Okay,
was an
okay.
issue. So essentially, like the both the TAs were, I mean, my links were being overwritten by the other TAs thing because they had only one sheet. So they were not aware that there were two TAs for this course. So
Okay.
that thing has been clarified. Going forward, you should be able to find the links. And since you asked, just give me 1 second. Let me stop sharing for just once. Yes, since you asked, let me share both the links in the chat for this thing. So, yeah. So you should be able to find the slides on this drive link. You can check right now to see if it works. And you guys should be able to see the videos over here in this list. So you can like open it and see if the things are available and tell me if there are any issues. The individual links will be available going forward from this week, along with the other discussion sessions links.
Yes, sir. They are available.
Uh, those things are all there, right? So yeah, you can go right ahead and revise through all these things. Uh, all right. So continuing now. So that is essentially the ballistic to diffusive transition. Now let us quickly talk about something that you guys would need to remember. So again, you guys have not seen the assignment for week 7. So this is something that you will study soon. So I will give you kind of an introduction so that you can go ahead and use this to solve your assignment problems. So that is the idea of realistic 1D and 2D channels. So what does this mean?
Sir,
What do I mean? Ah, yeah.
sir, screen share is not
Screen
given.
share.
Oh,
Yeah.
yes, yes, yes. I forgot to resume sharing. Um, so yeah, with this we shall end today's session. Yeah, so we have realistic 1D and 2D channels. So what does this mean? What do I mean by realistic? So the fact is, I mean, the sad fact that we have to deal with is all matter that is available to us is three dimensional. Even atoms have three dimensions. I mean,
Yes, sir.
the electron is distributed in 3D space. So if even my very atoms are 3D objects, then how can I have a 1D channel? What is the
Yes,
meaning
sir.
of a 1D channel? Then why did we do all the, like, I mean, thank you for saying yes, but why did we do all those derivations? I mean, have we been wasting our time?
No, sir. Uh, we kind of consider it because one dimension is very, very large. Therefore, we consider it
Yes.
as 2D and 1D channels.
Hmm. You're correct. So this is the essential question. It's not three dimensions, it's three dimensional. Realistic. So the answer to this question is, can we have a realistic 2D 3D channel? The answer to this is no. Sorry, an ideal 2D 1D 2D channel? No, we can't. So now what is a realistic 2D or a 1D channel? We will essentially have something like this. So I will have a what is essentially a 3D object, but one of the dimensions, as you guys rightly mentioned, is very small compared to the other two dimensions. So essentially, I will have something like this. So, and then I will have a very small thickness. Similarly, on this side, so this will have a width along this dimension. So I'm calling this a W, and it is going to have a length along this dimension L, and it is going to have a thickness. Oh, yeah, that is not the right symbol. What I should do is, yes, yeah, I'm trying to remember things I learned in engineering drawing several years ago. So yeah, I can do this and say, yeah, this thickness is some T. So we know that W comma L is very large compared to the thickness T. This implies I have an approximate 2D channel. And similarly, we can have a very large thing and a very small, yeah, and a very oops. Yeah, so drawing a 1D channel is much more challenging for someone with my level of motor control. Uh, so how shall I do it? Yeah, I should just draw it slightly bigger and assume that you guys will understand what scale is. Yeah. So in this case, I will have L is significantly greater than both W and T. So I again have a W, I have a T, and I have a length L. Is this clear?
Yes, sir.
So this is a 1D channel. Now I have a question to you guys. Is this just a relative measure? So if say T is uh, something like 10 nanometers, and if W and L are say 2 and 3 micrometers, can that channel be considered to be an approximate 2D channel?
Yes, sir.
Okay. So the answer is actually no. Because when we are considering an approximate 1D or 2D channel, the most important assumption is this. In the smaller dimensions, the electrons are assumed to be totally confined. Yeah, confined. Yeah. Always feels alien if I draw the line after. Yeah. Confined. God. Confined. So, what does that imply? Can you guys guess? Any ideas what I mean by totally confined?
Means, sir, in micro level, like energy levels are not discrete, but when the dimensions are at the nanoscale, all
Uh-huh.
the energy levels are discrete energy level.
Exactly. So essentially, what we do is when I say total confinement, this implies in the confined space, energy level, energy is strictly quantized. Like essentially, when we looked at a 2D channel or even a 1D channel, along the length of the channel, we assumed that the energy of the electron is somewhat continuous, correct?
Yes, sir.
Yes, sir.
But now that is no longer the case. Along these confined dimensions, the energy is strictly quantized. Okay. That implies, now what does that mean? That means, now if I write, so let us consider a realistic. The word we shall be using from now on is quasi or quasi, 2D channel. So let us consider this example. So in this case, what is happening? I have a very large surface area piled onto a very small thickness. Okay. So you will have, yeah, something like this. Again, W, L, and the thickness T. Okay. Now, what is the energy of the kinetic energy of an electron in this system?
Sir, half mv square.
No, 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 no. Like, come on. Like one of them is confined. Energy is strictly quantized. So essentially, like it is better to write the quantum mechanical version of it. So what I will write it as h bar square by 2m kx squared plus ky squared, which corresponds to the x and y motion of the particle. So let me also write the axes. So this is x. Why do I have to do that? I will throw my axis to the inside. Yeah. So yes, I will do this, and I will say x, y, and z. Okay. Plus, what is the other part of the energy? Like this is motion in the xy plane along this surface. What will the energy of the electron corresponding to its motion in the z direction look like? The energy is strictly quantized. So, what is a good approximation for it? What is a good model I can use? Go back to your first week. Can I treat it as a particle in a 1D box? Hello. Am I audible, guys?
Yes, sir.
So, did you get my question?
No, sir.
Okay, so essentially what I'm saying is now the electron, yes, has some kinetic energy. Now it can move freely along the x and y direction. Is that clear? According to this axis.
Yes, sir.
Right, sir.
But in the z direction, can it move freely?
No,
No,
sir.
sir.
Actually, thickness is very less. That's why.
Yes, so it cannot move very much along the z direction. So I can imagine that along the z direction alone, the particle is effectively stored in a 1D box, whereas in the other two dimensions, it can move freely. Is that clear?
Yes, sir.
Yes,
So
sir.
in that case, what I will do is I will just write this as n squared pi squared h bar squared upon 2m t squared. Now here kx comma ky are continuous values. And m is equal to 1, 2, 3, and so on. Is that clear?
Yes, sir.
So now the total energy of my particle is a combination of continuous values and discrete values. Okay?
Yes, sir.
So now how will the, so remember for a particle in a 1D box, how do the energy levels look like? The energy levels look like, this is my box, the energy levels
In
were
square E
some,
naught.
yes, so essentially, 4 E naught, 9 E naught, and so on and so forth, correct?
Yes,
I
sir.
have E naught, 4 E naught, 9 E naught, and so on. Now, how will the energy levels in this case look like? Try to visualize it. Or let me ask a slightly
Sir,
different
it
question.
will be
Ha,
continuous, but there will be sudden jumps in the graph
okay,
whenever that discrete amount of energy is added.
very good. So first tell me this, can this system, can the electron have zero energy?
No, sir.
Exactly, because n starts from 1. Kx and ky can be 0, but n cannot be 0 by our definitions. Okay,
Yes,
so
sir.
for a quasi 2D material channel. So, okay, by the way, what is a quasi 2D material? Can you guys give any examples? Are there materials that are
Graphene sheet.
naturally quasi 2? Huh?
अच्छा, graphene.
Very good. Yes, I heard because you guys have been mentioning graphene a lot of times before. So, graphene is a quasi 2D material. Another common example is molybdenum disulfide or any transition metal chalcogenide. So molybdenum telluride, or even some other transition metal with sulfur or tellurium will form quasi 2D materials. Okay, so these are, yes, their lattice is 2D, but again, there is a 3D substructure that is effectively confined in one direction and spreads out in two other directions. Okay, so these are two common examples of naturally occurring quasi 2D materials. But it is also possible to fabricate. We can also have a silicon quasi 2D material by doing, thin layer deposition or, several other techniques. Okay, so these are naturally occurring materials which can show this property. Now, how will the energy level look like? Essentially, what will happen is now I will have a minimum energy, some minimum energy, and above that, all energies are possible. Then, like by all energies are possible, I mean all the way up to infinity, because kx and ky can be any positive or negative values.
Yes, sir.
But there is the second jump after which again all levels are possible. Okay, so essentially what is happening is When I come to some energy that is greater than, so let me say the lowest possible energy is E naught. Okay. Between E naught to 4 E naught. Okay. What is the second energy? It is 4 E naught. Correct?
Yes, sir.
Now, between these two values, if I pick an energy, you can give me a range of kx and ky values that will give me a electron with that energy in this somewhere in this region. If I pick an energy in this interval, okay. Whereas if I pick an electron energy, like if an electron energy is lying in region 1, then only the kx and ky values can vary. If an electron has energy in region 2, how many combinations can I make?
Excuse me, sir.
Yeah.
Sir, can you repeat this part? My
Essentially,
network
what
was.
I'm asking is energy cannot be below E naught. Okay.
Yes, sir.
No electron with energy below E naught can be found. Now above E naught, if I pick a point, let us say above E naught but below E naught and 4 E naught. Okay. If
Yes, sir.
uh, E naught is less than E, which is less than 4 E naught, then only kx and ky can vary. Correct?
Yes, sir.
But what about here? If E naught 4 E naught, sorry, E naught is greater than 4 E naught, then what happens? I will have two cases. I will have the case n equal to 1 and n equal to 2. Do you understand?
Sir, how E naught can be greater than 4 E naught?
Sorry, I didn't know. I'm sorry. I meant E greater than 4 E naught. Really sorry.
Yes, sir. Yes, sir.
So now do you understand that there can be two cases? Like, see,
Yes, sir.
the particle can have a discrete energy of 4 E naught and the remaining energy can be available in kx or ky. Or it can have a discrete energy of E naught and the remainder of the entire energy can go to kx and ky. Both of those are possible.
Okay, sir.
Like, can you see that?
Yes, sir.
Because, see, from here, as I mentioned before, at this level itself, all higher energies can be achieved by choosing an appropriate kx and ky. Okay. But as my energy increases, I also have more choices to select the discrete level. So essentially what happens is in a quasi 2D channel, the number of K values, if you remember, the allowed K values increases because I have different choices for discrete energy levels. Like previously, if you remember, when we did the density of states calculation, only this quantity was considered for the 2D material. And starting from here, we did our density of states calculation and found out that density of states for a 2D material is a constant. But now what will happen is we have to repeat this calculation for each discrete energy level. Like we have to start from this discrete energy level and do a 2D density of states. We have to start at this discrete energy level and do a 2D density of states. We have to go to the third one, do another derivation for the 2D density of states. So because of this, the thing that will change is the DOS expression will get modified. Is that clear?
Yes, sir.
Like, can you, like, again, this is somewhat complicated. You will have to go through the lectures. I'm just giving you a kind of an intro to that. Okay, go through the lectures very carefully And next week we can have detailed discussions on this, because I mean, unfortunately, because of your timing and everything, you've not been able to go through the lecture content for week 7. So I cannot dive deeper into this, without confusing you guys. But what I will tell you is this, that because of my energy splitting into continuous and discrete parts, my density of states will change. If my density of states changes, then what changes? Will my current voltage relationship change? Will my ballistic conductance and ballistic resistance, all of these things change if the density of states changes?
Yes.
Yes,
Of
sir.
course it will. I mean, everything will change if the density of states changes. What you can see here is these different discrete energy levels are now defining kind of sub levels within this energy spectrum of my 2D material. So these sub levels are referred to as sub bands. So this is something that you will see in the end of this week's lecture. There are one or two problems that invoke the concept of sub bands. So how the density of states will change and all of these things will be covered in the lectures. So watch those things carefully. Try to address the questions. Again, if you have any doubts, you can post them on the forum. I will look at them and will answer them as and when they arise. Okay.
Yes, sir.
So here, yeah, they are both possible. Yeah. So with that, we will end today's discussion. So this is the last part that is covered. Like if you can see the things here for week 6, or rather week 7. Yes. So we talk about realistic 1D and 2D materials, conductors. So in that you will notice that again the same stuff that we have been discussing shows up, and we talk about, see, the energy, the discrete energy will show up, and then from there, so as you can see, only things are explained, there are no derivations. So the formulae will get modified, just understand how the modification happens, and that should be more than enough. Okay, and the final slide is essentially a summary of all the expressions you will require to solve the assignment questions. So I will give you that much of a hint. Most of the assignment questions can be solved by looking at just this one slide. Most of them. Some of the conceptual questions you will have to think, and based on that you can answer those questions. Okay.
Okay, sir.
Yes, sir.
Yeah. So with that, we come to the end of our session for week 6. So I thank you guys for joining this session and interacting. As I mentioned at the beginning, next week there might be a shift in the timing of this session, because I will not be available next Saturday. So I will have to get the dates straightened out with the folks over at NPTEL. So based on that, a new timing might be announced to you guys. In case that is not possible, I will upload a pre-recorded session. So at least for the next week, if you guys have any doubts or questions, please post them on the forum. And according to those questions, I will, address them one by one, and, post a pre-recorded session that, will probably have no participants. If a new time slot is made available, of course, you guys will be notified about that, and you guys can join up in that time slot, and we can discuss in real time. Okay, so that is all. So once again, thank you for joining in. We will meet
Thank you, sir.
whenever we
Thank
do
you, sir.
next week. The week after that, things will happen according to schedule. So yeah, that is that. So now I'm ending the call. Thank you and good evening.
Good, sir.